One other point I want to make when we're talking about a homotopy between two paths is that the underlying set matters. So let's say that we have two sets G, and maybe we'll call them G1 and G2 just so that we're clear here. And let's say that in G1 it's just going to be it can be a disk, it can be whatever kind of potato shape you want, but it's going to be what's called a simply connected set. And what that means is that there's basically no holes. I'll rigorously define simply connected in just a second, but let's say that I have a set G1 and it's just this region. And if I were to take a path, say I were to take a path like this, maybe it's kind of an ellipse path, I can continuously deform that basically into whatever path that I want. So, you could continuously deform it into a path, maybe like something over here. You could shrink it and then move it. Those are both continuous transformations. And in fact, you can do one better. You can even, if you want, take this, take your blue path or your red path, whatever, and then continuously deform it to a point. Okay, and so you can even continuously deform it to a point. And if your path has that property, so if gamma can be continuously deformed to a point, what we do is we call that contractible, and we write that gamma is equivalent to 0. So if, so we write, let me say this a little better. We write that gamma is homotopically equivalent to 0. This means that gamma is contractible, or gamma is homotopic to a point. And these are all going to be equivalent ways of saying the same thing, and that's that take this curve and you can continuously deform it until you get a really, really tiny curve that has no length, right? So it's just going to be a single point. And so those curves gamma are going to be called contractible or homotopic to a point, and we write gamma is equivalent to 0. Now, on the other hand, say I had another set G2, and this set is going to have a hole in it. So maybe, again, I don't care about whether we include the boundary or not, but G2 is just going to be this set, okay, not including the stuff that's missing from the middle. Now, if I were to take a path, gamma 1, this is no longer going to be homotopic to a point. So notice that this path, let's call it gamma 2. Gamma 2 is not contractible. And what that means is that there's no way to continuously deform this path to a point while keeping the path in G, right? It's important that the path stays in the set G the whole time, but there's no continuous transformation that can do that. The more that you shrink gamma 2, the only thing that it can really do is it can kind of wrap itself around the inside. It can kind of wrap itself around the inside of the path, right? You can maybe make it that small, but you can never contract it to a single point. And so the point of what I'm trying to say here is that the underlying set G matters. When we're talking about a homotopy, the two paths have to stay in G, and that can affect what's going to happen whether two paths are homotopic to a point, whether two paths are homotopic at all. I do want to point out that if I were to have another path, say gamma 3, and this path was to look maybe like that, now this path is going to be contractible to a point because since gamma 3 doesn't go around that missing region, you can contract it to that single point continuously. You can continuously deform it to the point. So you would say that gamma 3 is contractible. So gamma 3 is contractible. Gamma 2 is not. Okay, so the underlying set is going to matter. Now, I'm kind of going to, this is somewhat circular reasoning, but I think it's okay and I think it's clear. We're going to say that a set G is called simply connected. Simply connected just means that it has no holes. But now a precise way to say that, so a set G is simply connected if every closed path in G is homotopic to a point. or if every closed path in G is contractible to a point. Okay, that's what it means to be simply connected. That means that there's no holes in the set G, so that's just kind of the intuition there. Yeah, I think that's really all I wanted to say. So the homotopy of two paths depends on the underlying set, and then here's what simply connected means. So intuitively, simply connected means that it has no holes or that every closed path is homotopic to a single point.